Hi everyone, welcome to today's lesson. We are in Unit 5, Day 2. Last class, we learned how to prove that figures, especially triangles, were congruent by proving that all of their corresponding parts were congruent. We showed that if all of the corresponding angles were congruent and all the corresponding sides were congruent, then those figures were indeed congruent. Today we're going to learn two shortcuts for that, for triangles. So when I say a shortcut, I mean a way that we're allowed to prove triangles are congruent without having to prove all 6 parts are congruent, without having to say all 3 sets of sides are congruent and all 3 sets of angles are congruent. The first shortcut is called the side-side-side congruency theorem. Side-side-side meaning as long as all 3 sides in your triangle are congruent to the 3 sides of another triangle, then you're allowed to immediately say that those 2 triangles are congruent. So if AB is congruent to DE, and if BC is congruent to EF, and if AC is congruent to DF. So as long as you have all 3 sets of sides congruent, then you're allowed to say that those triangles are congruent. Triangle ABC is congruent to triangle DEF by the side-side-side congruency theorem. Remember, order of letters does matter, so make sure you write the names of those triangles correctly. So in a proof, right, you're going to be given a given. PQ congruent to ST, that was our first given. And this is QR congruent to RT. Oh, that was our second given. So in this one, they're putting the givens all on different lines. That's okay. R is the midpoint of PS. Oh, that was the third given. So far, so good, right? Now here's a vocabulary word, midpoint. Midpoint means that it's in the middle. R is in the middle of segment PS. So that means that PR has to be congruent to SR. That's the definition of midpoint. Okay, so the givens told us that PQ was congruent to ST, that QR was congruent to RT, and we just proved that PR was congruent to SR. I now have all 3 sides of one triangle congruent to all 3 sides of the other. So I'm allowed to say that those 2 triangles are congruent by side-side-side congruency. And another proof here. This is that JL is congruent to MN. So that's given, and I'm going to mark that in the picture. JL congruent to MN. And then it says that K is the midpoint of JN and LM. So that's given. K is the midpoint of JN. Well, if K is the midpoint of JN, that means that JK and KN have to be congruent. So this is the definition of midpoint. But it also says that K is the midpoint of LM. So that means these 2 have to be congruent also. So that's the definition of midpoint. Again, you can use the same reason as many times as you need to. And with all of that, I now have all 3 sides of one triangle congruent to all 3 sides of another triangle. So I can say that those 2 triangles are congruent by side-side-side. In my third example, AC is congruent to AD. That's given. And I'm going to mark that in the picture. AC congruent to AD. CB is congruent to BD, and we'll mark that in the picture also. And now I need another way to prove that third side is congruent. Oh, but do you notice that they're sharing that side? We know that AB has to be congruent to itself, and we know the property that says that anything is congruent to itself. Remember that reflexive property? Oh, that's going to come back a lot in this unit. So AB is congruent to itself. A lot of the times I'll tell students that if you see 2 triangles that are squished up against each other, it might be a good idea to redraw those triangles. So triangle ABC and triangle ABD. And I usually redraw them so they're facing the same way. AC and AD were congruent, CB and DB were congruent, and we just proved that AB and AB were congruent. So I'm now allowed to say that triangle ABC is congruent to triangle ABD by side, side, side. Because I've proven that all three sides of the first triangle are congruent to the three sides in the second triangle. The other shortcut we're going to talk about today is the side angle side. Side angle side says that two sides in the included angle of one triangle is congruent to two sides in the included angle of another triangle. So in this case, we can say that AB is congruent to DE, and the other side would be BC and EF. So I'm going to write that down here. And when we say included angle, that means the angle that's touching both of those sides. So that would be angle B and angle E. If that's true, then you can say that triangle ABC is congruent to triangle DEF by side angle side. Included means the angle between the sides. Remember that. Okay. So let's look at some examples with side angle side. Oh, see how these two triangles are squished up against each other? I'm just going to redraw them. They don't have to be perfect, but I think the redraw can definitely help later when you don't know which theorem that we're using. So I have J, M, N, and notice I redrew them so they were facing the same direction. If you're not sure what to label the other triangle, look at the names of the triangles. J corresponds to L, M corresponds to N, and N corresponds to M. The given says that JM is congruent to NL. So I mark that in my picture. And the other given says that angle JMN is congruent to angle LNM. So JMN is congruent to LNM. There they are. Notice that these two triangles shared a side. They shared MN. So MN has to be congruent to itself. That's the reflexive property. So I'll mark those congruent. And now I have two sides and an included angle that are congruent. So I'm allowed to say that these two triangles are congruent by side angle side. In example 5, the given says, oh, before I do that, redraw your triangles. Triangle ADB, triangle A corresponds to C, D corresponds to itself, and B corresponds to itself. All right, AB is congruent to BC, that was given. It says BD bisects angle ABC, that was given. And now I see this vocabulary word, bisect. BD bisects angle ABC. That means that these two angles have to be congruent. So in my picture, that would be here. So angle ABD is congruent to angle CBD. That's the definition of an angle bisector. Well, those two triangles shared a side, so we know they're equal to each other. That's the reflexive property. So here's one of Mrs. Grandy's secret tips and tricks for writing proofs. Anytime you see triangles that share a side, you're going to want to use the reflexive property. I have seen very few proofs where the triangles share a side and you didn't need the reflexive property. So reflexive property, anytime you see the triangles share a side. Well, now look in your redrawn triangles. You have two sets of congruent corresponding sides. You have the angle in between congruent, so we can say these triangles are congruent by side angle side. Another example, V is the midpoint of WZ and XY. You may redraw these triangles if you wish. They're separated enough for me that I can leave them that way, but if you feel like you want to redraw them, please definitely go ahead and redraw them. All right, we have that midpoint word. V is the midpoint of WZ. That means that these two pieces have to be congruent. V is also the midpoint of XY, which means these two pieces have to be congruent. So when it says VZ is congruent to WV, that's going to be your definition of midpoint, since V is in the middle. And I'm going to skip 3 for a second. It says XV is congruent to VY. That's the other definition of midpoint. Since it was the midpoint of two segments, we can probably assume we'll use that definition twice. Number 3 says angle WVX. WVX, well, that's right here. It's congruent to angle YVZ. That's right here. Why would those angles be congruent? They're vertical angles. Vertical angles are congruent. So now why are those two triangles congruent? Well, those two triangles are congruent because they have two sets of corresponding congruent sides and the included angle is congruent. So this is side angle side. Another example, oh, I see two triangles sharing a side there. I'm going to redraw them, and in the back of my mind, I'm going to know that I have to use the reflexive property. All right. So let's label these triangles H, G, J. And looking at the names of the triangles, H corresponds to J, J corresponds to H, and G corresponds to I. The given says that HI is congruent to GJ. So we'll write given HI congruent to GJ. I think I drew my triangles wrong. GJH. I did. I put my H and my J in the wrong spot. Let me try that again. And why does it really matter? Well, I just like my triangles to look the same so I know that I can prove them congruent. So let's see. G, J, H, I, H, J. H, I, G, J. There we go. That's better. Now, it says that HI is parallel to GJ. Why on earth would we care about parallel signs? Well, as soon as we know that HI is parallel to GJ, well, now I have a transversal, and all of the relationships from parallel lines are fair game. Corresponding angles, alternate interior angles, alternate exterior angles, consecutive interior angles. It's all fair game now. One thing I will say that in a picture like this, my number one go-to would be alternate interior angles. That's usually the one that's used the most. See my alternate interior angles there in my triangles. If I were to delete all those extra lines, you would see, yes, these are alternate interior angles now. And we know that alternate interior angles are congruent as long as the lines are parallel, which they are. So these two angles are going to be congruent because of alternate interior angles. All right, so now it says HJ is congruent to HJ. Well, we know that anything is congruent to itself by the reflexive property. And hopefully, as soon as you saw these two triangles right up next to each other, that reflexive property came to mind. So put all this in our picture. HJ is congruent to HJ, and angle GJH is congruent to angle IHJ. I see two sides with an angle in between, so these two triangles are congruent by side angle side. All right, now what if they give us points on a coordinate plane? Can we prove that those triangles are congruent? Absolutely. Remember, side, 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 and especially the side, 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 we need to prove that all three sides of one triangle are congruent to the three sides of another triangle. And congruent means the same length. So what we can do is find the length of all of the sides of each triangle, and if they match, then they're congruent. So we need to use our distance formula. Remember that distance formula? If you don't, you might want to look it up. But the distance formula is the square root of, we'll say, x2 minus x1 squared plus y2 minus y1 squared. If you don't have that memorized by now, you want to make sure you get that memorized because that comes up a lot. So for PQ, we're using the points 5, -4, and -3, 7. So your x2 would be -3, your x1 would be 5, y2 is 7, and y1 is -4. The biggest mistake that some students make is they forget to square their parentheses. Okay, so -3 minus 5 is -8. A -8 squared is 64. 7 minus -4 is really 7 plus 4. 7 plus 4 is 11. 11 squared is 121. And 121 plus 64 is 185. Leave it square root 185. Okay. So if at this point you're jumping straight to your calculator, that's fine. Don't put the square root symbol in. Just carry that square root symbol with you. And the reason why is because this is your exact answer. If you have to round it, it's not exact anymore. So just leave it square root 185. So then we're going to find the length of QR. So now we're using -3, 7 and 0, 2. And we're going to take those numbers and plug them in to our distance formula. And does it matter which order? Which one do you make x1, y1? And does it matter which one you make x2, y2? No, it doesn't matter. If you do them in, if you pick one point to be your x1, y1, and someone else picks the other point to be x1, y1, you're still going to get the same answer. So if you set it up differently than I do, but we get the same answer, that's okay. So let's see, 0 minus -3 squared, 2 minus 7 squared. Well, 0 minus -3 is really 3. 3 squared is 9. 2 minus 7 is -5. -5 squared is a positive 25. 9 and 25 is 34. So QR is the square root of 34. PR, we're going to use point P and point R. 0 minus 5 squared, 2 minus -4 squared. 0 minus 5 is -5. -5 squared is a positive 25. 2 minus -4 is really 2 plus 4. That's 6. 6 squared is 36. So we're going to add 25 and 36. We get the square root of 61. Go ahead and find the length of xy, yz, and xz, and leave it in the radical. Don't round it. You don't even have to simplify the radical. Just leave it in the radical. So after doing your distance formula 3 times for that triangle, you should get the square root of 185, it's the length of xy. The square root of yz is, the square root of 61 is the length of yz, and the square root of 34 is the length of xz. Notice I drew some triangles over here, and I matched up those lengths. 185 equals 1, or square root of 185 equals the square root of 185. The square root of 61 and the square root of 61, the square root of 34 and the square root of 34. So are these triangles congruent? Yes, they are. By side, side, side. And now we need to write a congruency statement. A congruency statement is triangle, letter, 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 is congruent to triangle, letter, letter, letter. And the order of the letters does matter. So you can name the first one how you wish, PQR. But then when you name your second one, you need to name it so that the corresponding letters actually do match up. So when I redrew it, I needed to redraw it in a way so that the square root 185, the square root 34, and the square root 61 were in the same position. And the only way I could do that was if I put a Y here, an X at the top, and a Z over here. So triangle PQR is congruent to triangle YXZ. If you need to see the work for any of that distance formula, or you would like to see this answer written as a sentence, you are welcome to check out the key posted to OMHS. I'd like you to try number 2. You have to use the distance formula 6 times. I know it takes a little bit of work, but it's not hard, so that's good. And then I want you to tell me if your triangles are indeed congruent or not. So try that now. So you can see my answer for each length here. PQ, you should have gotten the square root of 221. QR is the square root of 232, and PR is the square root of 41. And when I went over to XY, I got the square root of 221. That was promising. But then for YZ, I got the square root of 82. That didn't match. So I started thinking, they're probably not congruent. And then for YZ, I got the square root of 101, which definitely doesn't match. So no, these are not congruent triangles. They don't have pairs of congruent sides. These sides would have to match up and be the same length from one triangle as in the other triangle, and they're not. So these triangles are not congruent. All right, that was today's lesson. Don't forget to do the attendance quiz, and don't forget to do the exit ticket. The attendance quiz was given to you earlier in the lesson. And I hope you have a wonderful day.